And it's still worse. There are still other problems. So if you take a look at this program, then we see in count 2 that there are no function calls during this while loop. And as we said from earlier in the semester, the optimizer in the C compiler is able to say, well, there are no function calls in between this iteration. I can really just add n to the counter, or I can at least just keep counter in a local variable. And this waiting over here, again, there are no function calls, so the compiler can say, if it doesn't pass the first time, it'll never pass, and it just loops forever. And this is part of the definition of C, the contract that we make between programmers and C compilers. We saw that there is a possibility of putting volatile in front of this counter, which will force the optimizer to treat, to not make any assumptions about when a global variable can change. That would cause these programs to behave differently, but it's not the right answer for concurrency. Right. So whenever you have sharing, when you have threads and sharing, we're going to have to do something explicit. And volatile is not explicit enough. We'll have to do something explicit to say these things are shared, they need to be handled in a particular way to make sure that it makes sense for multiple threads to update. And when we use proper synchronization constructs, then we don't have to worry about what's atomic or not at the machine code. It doesn't matter whether we compile with -02 or not. When we use that right kind of synchronization, it's going to make sure that caches are forced to be coherent at the needed time. And it's also going to make sure the compiler knows that these variables that are explicitly synchronized in the right way, variables, other memory locations, that they might change outside of the synchronization points. So, you could try to reason about the machine code and optimization levels and so on, but the bottom line is if you're writing C code and you have a race condition, you just don't know what the program does. You have to use some more explicit synchronization to make it work. There are several approaches of dealing with the problem of sharing. One is don't do it. Instead, stick with something like processes, or even if you use threads, don't have those threads modify the same data. You can make this work by having all communication go through messages. So for example, if threads need to work together to arrive at a count, then they all need to send accumulated counts back to some other process that's responsible for adding them up, like the main thread or something like that. The advantage of this approach is that when you're writing code that runs in a particular task, you don't have to worry about other tasks modifying the data that you're looking at or race conditions on modifying data. The potential drawback is that you have to arrange your code in a certain way. Depending on what you're doing, organizing your program around the sending and receiving of messages can actually be a good structuring technique for your program, but it's not for all programs. But it's not always the most convenient way to do things. Another possibility is to say that the problem stemmed from different bits of code not being atomic, and you would like to have a system there you can just say this should run atomically, and the runtime system or the compiler figures it out for you. That would be a transactional system or transactional memory, much the same way it works in databases, where a programmer really can say, figure out some ordering to make this code appear to be atomic with respect to other processes. And usually a transactional system will need the ability to rewind an attempted atomic operation so that it can retry it in a different way with a different ordering and other tasks. And that means that transactional systems requires a lot of extra machinery in the runtime system, in the operating system perhaps, or maybe even in the processor, depending on how it's done. Finally, there's the approach of using locks. So with locks, a programmer doesn't quite get to say this runs atomically. What the programmer says is, don't do this kind of ordering. Don't let code go here when other code is here, something like that. So it's almost like declaring atomicity, but it turns out not to be quite that. In fact, declaring locks correctly to get the atomicity that you have in mind can often be difficult. But by taking responsibility, the programmer doesn't need as much machinery from the runtime system and the underlying processor. And for that reason, locks are especially common for systems programming. And this is the approach that we're going to look at for the rest of today.